These are the notes for Chapter 18 from the McGraw-Hill text, and would be the first day. So with Chapter 18, we're talking about acids and bases. First item of business would be, let's kind of define and find out the properties of acids and bases. Acids, for most of the acids we deal with, they are going to be substances that have an H in the first slot, the positive slot, H+, and they dissociate to put H+ into solution. There are some exceptions to that, but most of them will fall into that category. Most bases, when you draw a line after the first capital letter or right before the second capital letter, you look at the left. If it's an H, it's an acid. If it's not, look to the right. If that's an OH, it's a base. If it's not either one of those, then you don't have an acid or a base, and you're dealing with a salt or some other substance. So we'll talk about properties of acids. Acids are electrolytes, and they conduct electricity. They dissociate H+ into solution, and all acids are electron acceptors. Acids turn litmus red. Like we said, they're electrolytes, conduct electricity. The magnesium and zinc react with acids to produce H2 gas, and we've done that in several labs where you actually lit the hydrogen and it popped. Those properties of acids. Base properties. They form electrolyte solutions, just like the acids. They're electric conducting. Bases turn litmus blue. You can remember B for base, B for blue. Bases taste bitter, where acids tasted sour. And there are differences between bitter and sour. Bitter's sensed on the back of your tongue, and that's the taste like when you have aspirin or milk of magnesia. Those are some medications that have a bitter taste. Of course, sour is like lemon juice. Most bases dissociate to release OH into solution, and bases are all electron pair donors. So we're going to talk about the three acid-base models, and we do this for a couple of reasons. One, so you get a better understanding about acids and bases, but second, so you get a better understanding about how science works, because the way science works is somebody will propose a model or a hypothesis, they put this out there, and they fully expect that somebody's going to look at it and say, well, here is something we can do to improve your model. We start out with Arrhenius acids and bases. Arrhenius, there really wasn't a good solution to what an acid or a base was, so he took large quantities of these, or small quantities of a large number of acids and bases, set them out in his lab, and then he did experiments. What he found out was at least the acids he had all had H+. The bases he had all had OH and dissociated OH to solution. So that gives his idea in his model of what an acid and a base was. You should know these for each of the models, what an acid and base are. Arrhenius acid dissociates to produce H+ to solutions. Arrhenius bases dissociate to produce OH. Now, we talk about examples: HCl, hydrochloric acid, H2SO4, which is sulfuric, H3PO4, which is phosphoric acid. You should review over your acid naming rules, because we are going to, for this test, I'm going to review over that and have you name some acids also on your review. Bases don't have any different name than you would normally see, and yes, bases are just as dangerous, but they don't have special names. So examples of bases: NaOH, which is sodium hydroxide, MgOH2, which is magnesium hydroxide, and AlOH3, which is aluminum hydroxide. Notice that we just say the first positive ion name and then the hydroxide. So there's no prefixes. Now, you notice that we had sub-2s and sub-3s on some of the H's and also on some of the OH's. Well, for the H's, for the acids, that number can classify it. If we have H Cl, that would be a monoprotic because of one hydrogen. H2SO4 is diprotic because the 2 below the H. H3PO4 is triprotic. And that term protic comes from the fact that H plus started as H with one electron and one proton. When the electron goes away, all we have left is a proton. So H plus is actually a free proton that's floating around. Mono, di, and triprotic. So the second model that we're going to talk about is the Bronsted-Lowry model. And Bronsted-Lowry came up separately on their own about the same time. And keep in mind that it wasn't just accidental that they were doing research on this, that when Arrhenius published his results, these guys all looked at that results and said, now wait a minute, you know, we know something that doesn't work with that model. We're going to try to improve on his model. They came up with the idea that, especially because of NH3, ammonia, the base, did not have an OH, and they knew it was a base, turned litmus blue, so there's something else happening. So what they decided was that Arrhenius had kind of a good idea, but that he had the wrong idea on the bases as to what caused the bases to be base, and that was that bases were bases because they were hydrogen ion acceptors. And they thought, well, this works real well because all of Arrhenius's bases had OH, and OH is a hydrogen ion acceptor. And when it accepts hydrogen, it becomes water, HOH. So, you know, they did not really change the acid part of his model. They just reworded it. Their idea of acids are the hydrogen ion donors, and bases are hydrogen ion acceptors. Now, a big part of this is being able to do some of the conjugate acid-base pairs. Notice that we have some of them down there at the bottom of the page. There's some really good examples in your book, and I'm going to go over an example on the board here in a second. There's also some on your foldable that you'll be working on for extra practice. And what the conjugate acid-base pairs are, remember that to be an acid, it gives an H. To be a base, it accepts. So what they did is they have an acid that donates and a base that receives, and then we, of course, show the product of that on the other side. And we're going to connect with a bracket the conjugate pairs, like when one gives an H, it ends up with one H less. You're going to connect those with a bracket. When one accepts an H, the model on the other side ends up with one more hydrogen, and you connect those with a bracket. Way to do these is to remember that on each side of the arrow, there's an acid and a base. On each end of the bracket, there's also an acid and a base. And this will make it work real well as far as being able to set up the acid-base pairs. One other thing, on the bottom of this page, the Bronsted-Lowry, about the middle point of the page, you see H3O+. You need to know that H3O+ is hydronium. Every hydrogen, when it goes into solution, the hydrogen connects with water, which is HOH, and becomes H3O+. Remember, water is neutral, so it's got a neutral charge. When we bring the plus in with the H, it ends up being H3O+, because now you've got 3 pluses and 2 minuses. So that's hydronium. You need to maybe make a flashcard or highlight that in your notes so you know what it is. So we're going to talk, before we get to the Lewis model, we're going to go over an example. And a good example would be HCl plus HOH. Okay, so we've got HCl, and we know that when we draw a line before the second capital letter, there's an H, that's an acid. So we're going to label it acid. Well, if that's an acid, then this needs to be a base because there's an acid and a base on each side of the arrows. Okay, now we're going to put a bracket to the other side. Well, if this is an acid, it donates an H. What's left if it gives up an H+? Well, of course, a Cl-. Because remember, H+ and Cl- make it neutral. If the H+ goes away, now it's Cl-. Well, there's an acid on this end of the bracket. What's on the other end of the bracket? a base. So that's the first one. Now, if this is a base, well, you know that the base is going to accept a hydrogen. That's what makes it a base. This hydrogen is going to go to that other substance, which makes it H3O plus. If that's a base, then this has to be an acid. Because remember, there's an acid and base on either side of the bracket, and there's an acid and base on either side of the arrows. So there we go. We've labeled the conjugate acid-base pairs, connected them with the bracket. You need to be able to do that. So we move on to the Lewis model. Y'all remember Lewis? He gave us the Lewis dot diagrams. The Lewis dot diagrams are the way that we show how electrons affect bonding in atoms and compounds. But Lewis looked at this model. Again, Bronsted Lowry posted their models, and they talked about them. This is how they got science out to the public. They didn't have the internet, but books and publishing was not really at its peak at that time. So they would go to places like France or other consortiums or places where they put groups of science people together, and they would have these conventions where they would present their ideas. Well, so Lewis took this and said, you know, the electron's responsible for so much in chemistry. I think it's also responsible for acids and bases. And what it comes down to, that's really what makes an acid and a base a base. So you need to know all three of these models. How do we know these models, or how do we remember these models? Well, you know, on the first two, acids were H donors, basically, even though it was worded different. Arrhenius said that acids dissociate to put H plus in solution, and Bronsted Lowry said acids are H plus donors. Somewhat the same. Arrhenius, OH, was dissociated on bases. Bronsted Lowry said that bases were H acceptors. Now, it's going to kind of be crossed here because the acids are the acceptors and the bases are the donors, but it's not H pluses here, it's electrons. So the way to remember it, this will help you remember it very well, is to remember that H plus does not have any electrons because it started as H with one electron, and here's our H with one electron. When that goes away, okay, minus a minus, we end up with H plus. What can H plus do with electrons? The only thing it can do is it can accept a pair of electrons. There's Cl. It's in column 7. It has 7 electrons. It gains one, and we use a triangle to represent that. And now it was neutral. It gained one. It's Cl minus. This pair of electrons is donated, and that makes it a base. H plus can't do anything with electrons but accept because it has no electrons. That makes it an acid. So if you remember, H plus is acid, and it's always associated with acids. H plus has no electrons, so it has to accept. That'll help you remember the Lewis model. Now notice on this example I gave you that BF3 is an acid. You need to be able to recognize compounds that accept an electron pair as acids. Compounds other than H are substances other than H plus. So look over that. Make sure you can see why BF3 is an acid and the other compound's a base. As far as strengths of acids and bases, one of the questions I'm going to ask you on the free response part is compare or explain what strength of an acid is and concentration, and compare and then say what they have in common also. Well, first of all, strength of an acid is how much the acid splits. It's like if I had a box of these and they were all super glued together except for one, this representing the H plus in an acid, that would be a weak acid because only one put H plus out here. The rest are all glued together and you can't get them apart. So they're really not functional. Well, that's what a weak acid is. It's not very functional as an acid because it's got a strong bond between whatever the X minus is, Okay, it might be acetate. Acetate holds on to H pluses real tightly and makes acetic acid, which is a weak acid. About 1% of its H pluses break free. Well, if only a few of the H pluses get out here and do what acids do, well, then it's not going to do much of the acidity properties. So that's a weak acid. Weak acids don't split much. Strong acids split usually 100%. So like everything splits, lots of H pluses out there. Concentration, on the other hand, is how many moles per liter of acid we have in solution. So it's kind of like how many markers we have, whereas strength is how many of them split and are functional. Know the difference. And then what do they have in common? Well, if you have a concentrated strong acid, it's going to put lots of H pluses out, not just because they all split, but because there's lots of them. So the amount of H plus that results is kind of common to both of these concepts. You've got to have some out there in concentration in order to have some large number that will split. If you've got a dilute acid, even if they all split, there's not going to be very many H pluses. So they both have this common product of how many H pluses they produce. So Ka and Kb are our next concept, and this is what tells us strength of an acid or base. Ka for acid, Kb for base. We're going to talk about Ka, even though Kb is basically the same thing. It's just kind of modified a little bit to deal with bases. When we talk about the Ka and Kb, the Ka is like a KEQ. How do we start out for Ka? Well, the first thing you do is you write the acid and then show how it dissociates. Now we're going to do HCl. HCl is a strong acid and it dissociates 100%. These Kas are mostly used for us to figure out how strong weak acids are, but that's okay. It can be used with a strong acid too. So HCl, draw a line right before the second capital letter, and that gives us H plus plus Cl minus. Now we write the Ka expression. Ka equals product concentrations multiplied over reactants, just like KEQ. So we draw our line, and we've got H plus, brackets, which means moles per liter. Remember, the brackets are separators, but they're also moles per liter. They're our unit, times Cl minus over HCl. Product multiplied in brackets over reactants. So we know that H and Cl are going to be equal. Why is that? Well, it's the pin and cap concept. Every time a pin and cap separate, you got one cap and one pin. Every time HCl separates, you got one H plus and one Cl. So they're equal in numbers because they have a common source. So when you're given H plus, you also know Cl. You'll write that same number in both of these brackets. The bottom number, a little bit more complicated because it's not just plugging a number in. So for example, in this example, we've got 0.100 molar HCl originally. But remember, this is a KEQ, an equilibrium statement. So it is the situation once it's in equilibrium. And it's not the beginning situation. So what the rest of the problem tells you is that 0.001 molar of hydrogen splits off from the original situation. So we know that the H and the Cl are both 0.001. But we also know that we started with 0.100 molar HCl. We don't need to write the molar because the brackets tell you that. But we don't have 0.100 anymore because what happened? Minus 0.001, that split. So once we get to equilibrium, after the H is split off, that's what we have left. It's kind of like having a box of 100 markers and you take one out. We want to know, once we're using them, how many are left? Well, there's 99. We've subtracted the 100 minus the one we're using. Well, same here. So the way you're going to do a Ka is you're going to write Ka equals the product, the two ions, over the whole, and then you're going to plug in the H plus for the two top numbers, and you're going to, for the bottom number, you're going to plug in the beginning amount minus the H plus. So H plus is going to appear 3 times here. It's going to appear multiplied on top, and then the beginning amount minus the H plus down here. Don't forget to subtract that amount. You get through, you'll get a Ka value. Kas generally for a weak acid will be like 10 to the negative 5th, 10 to the negative 7th. For a strong acid, usually they're going to be 1 or bigger, because remember, the more parts you have, the stronger the acid. And if the numerator is bigger, then it's going to be greater than 1. So keep that in mind. When we calculate Kas, there is a chart in the book that has Ka values, so you can look at what the strengths of some of the weak acids are. Kb, again, very similar, except you're going to have the beginning, whatever the positive ion is, with OH, and then at the bottom you'll have that together, and you do the same process as far as solving for it. So that finishes our notes for that first section. Remind you that there are some practice problems on your foldable. There's also some problems on your review. Read through the chapter if you haven't, and try to go through these notes. Stop them if you need. Maybe look in the book for examples, then start it up again. Study hard, work problems, and good luck.